Hello, everybody. This is your first video for section 2 on unit 6. So this section deals with sampling distributions of means, of sample means. So what I'm hoping you'll see throughout this video and the next video, which is just practice problems, that there is a great deal of similarity between what you did with proportions and what you're going to do with means. Okay, so a lot of the processes are going to stay the same. It's just some of the formulas and one of the conditions that you have to check changes a little bit. Okay, so let's go ahead and jump into it. Okay, so we've already looked at sampling distributions of proportions. So the other common type of sampling distribution is of means, of averages, which is actually the most common. It's more common to see studies that deal with sampling distributions of means rather than proportions, just because a lot of the data that we like to gather on things is quantitative rather than categorical, right? So what we're going to do in class is very similar to what we do with proportions, work with an applet that will help us figure out what happens when we change the sample size, when we're pulling means from a skewed population versus an already normal population, right? So we're going to answer a lot of the questions that you see on the left side of your screen. Okay, so I'm hoping that you're watching this video after we've done that, so it doesn't give anything away, right? But I'm going to talk to you about, in this video, properties of your sampling distributions of means. And we're also going to talk about something called the central limit theorem, which is it's like the golden rule of statistics, right? So let's go ahead and talk about it, okay? So very similar to proportions, right? What sampling distributions of a sample mean show us is it tells us how well the sample means, right, from many different samples that we pull. Remember, sample means are X bar, which I'm going to have to put a little bar over in my notes on the side. Okay, so it tells us how well the sample means estimate the true, and it should say mean on that slide. Wow, terrible. The true mean, okay, which is represented with that Greek symbol mu. So give me 1 second. Let me put my bar over the top of my x bar, and the true mean. So like I said, this should say mean right here. Not sure how I missed that when I was putting these together. So that should say mean right there, okay? So if you recall from the last section, which was all about proportions, we use those with categorical variables. So means are used with quantitative variables. Okay, so that's a good rule of thumb is anything that you can take an average of or anything that has a unit, okay, is a quantitative variable, all right? So the formulas for mean and standard deviation are a little bit simpler than the proportion ones, okay? But I'm hoping that they look familiar, okay, at least. Okay, so the mean of the sampling distribution of means, okay, so it's the mean of means, which is a little meta, right? But the mean of the sampling distribution of means is just the true population mean, okay? So that's what, right, this value here is the population mean. Okay, and then for standard deviation, okay, your formula for the standard deviation of the sampling distribution is the true population standard deviation divided by the square root of n, right? Keeping in mind, like I said here, that this symbol is your population standard deviation. Okay, and then n, as always, is your sample size. Okay, now like I said, I'm hoping that these look somewhat familiar and you can make a connection back to what we did with proportions, right? The mean of the sampling distribution of proportions was the population proportion, okay? And then standard deviation's a little bit different. When you're dealing with quantitative variables in the problem, they have to give you the population standard deviation, otherwise you can't solve the problem, okay? So where these formulas come from, right, and what's important to note about them is that they are true for any population, regardless of shape. Okay, and that's a key thing, that's a big thing, right? If you remember, when we dealt with really skewed proportion populations, like a distribution of proportions, that sometimes, okay, sometimes if it was skewed too much and the sample size was too small, then we couldn't continue with the problem, right? Because one of the conditions wasn't met. Okay, so these formulas for mean and standard deviation are true for any population, regardless of if they are normal or not, as long as the 10% condition is satisfied. Okay, so that's the rule, that the sample is no more than 10% of the population. Okay, so remember, the way that we would figure that out is, let me write it out like this. The way that we would figure that out mathematically is we would do 10 times the sample size and ask, is that less than the total population? Okay, so the 10% condition here basically gives us permission or allows us to use these formulas for mean and standard deviation. Okay, that's essentially what it's for. Okay, another thing, okay, that's a little bit different from when we were dealing with proportions is what happens with the shape of the sampling distribution. Okay, so the shape of the sampling distribution of sample means depends on the shape of the population. Okay, so if the population is normal, then the sampling distribution will also be normal. Okay, of means, I should say sample means, is also normal. Very important, no matter what the sample size is. Okay, now that's a little bit different than what we dealt with proportions. You probably saw when we had really, really small sample sizes, the sampling distribution looked kind of normal, but maybe not quite normal, right? But for means, right, if the population is normal, the sampling distribution will also be normal, no matter what the sample size is. Okay, for a skewed population, okay, if the population is skewed, then the sample size matters. Okay, and the key thing from this is that larger sample sizes mean a more normal shape. Okay, which again is a little different from proportions, right? Obviously, this rule, that larger sample sizes mean a more normal sampling distribution, that also held when we were talking about proportions. Okay, that was also true there. But you'll see when we do more problems with means that that this idea for shape of a sampling distribution works out a little bit differently when you're dealing with means, but it's the same general idea. Okay, so just to sum up for you, okay, we have these formulas for mean and standard deviation. For both of these, you have to know the population mean and the population standard deviation. Otherwise, you can't solve the problem. Okay, the formulas work only when the 10% condition is satisfied. So that condition basically gives us permission to use these formulas for mean and standard deviation. Okay, and then shape depends on the shape of the population, okay? If the population is normal, sampling distribution will be normal, no matter what, okay? Even if the sample size is really small, like 2, okay? And then for a skewed population, you have to have a large enough sample in order to get a normal sampling distribution. So then the question becomes, okay, well, how big is a large enough sample, right? Because honestly, in the real world, right, or strike that, in the perfect statistics world, right, or in perfect math land, we get data a lot of the time that is normally distributed, right? Which that actually is not as common as you would think in the real world. Okay, a lot of data that we look at ends up being skewed in one direction or the other. Okay, so if we are going to try to pull a bunch of samples and try to figure out what the true values are, right? Meaning what's the true mean and the true standard deviation, we have to have sample sizes that are big enough. So then the question for statisticians, like I said, becomes, okay, well, how big is big enough? Okay, and that brings us to something called the central limit theorem, okay, which we often call the fundamental theorem of statistics, okay? So this is the central limit theorem. It states that a sampling distribution of means, right, or a distribution of sample means, distribution of X bar, is approximately normal if these 3 conditions are met, okay, which I'm hoping look a little bit familiar to you, since we've already talked about some of these when we were dealing with proportions. Okay, so your first condition is, 1, that you have a simple random sample of the population. Okay, so that each sample that's pulled is a simple random sample. Okay, that's your randomness condition. Okay, the second condition I called is I typically will call the 10% condition, but you'll also hear it called the independence condition. Okay, so that's where okay, either you have samples that are independent of one another. Okay, so that would be like if you rolled a dice, right, lots of times. Say you rolled 2 dice and found average the average number on the dice that you roll, right? If you do that over and over and over again, each of those samples is independent of one another, right? But in a real world study, when you pull samples and you eliminate people from that sample after you gather their data, right? The population proportion, or sorry, the population mean changes a little bit. Not very much if you're dealing with a big enough population, but a little bit, right? Because you're not going to sample someone that you're not going to sample someone again that you've already sampled, if that makes sense, right? So those individual samples, technically, if you're not putting people back into the population to be sampled again, they are not technically independent of each other. But that's where the 10% rule comes in, that we're saying if we don't take too many people out of the population, then it's not going to affect the average enough for it to be a big deal. Okay, so you have independent samples or the 10% condition is satisfied. Okay, again, and that's where the sample is no more than 10% of the population. Okay, and then the last condition you'll remember from proportions, I called success fail. Okay, because when we were dealing with proportions, you had the number of successes. You had a formula for number of successes and a formula for number of failures. Okay, with means, some people will call it success fail, and typically you'll hear me call it success fail, but other people will call it the large counts condition. So same thing, okay? Success fail, large counts, it means the exact same thing. Okay, so if you remember from proportions, okay, the 10% condition was, is my sample too big? Like making sure that the sample isn't too big. And then in this condition, the success fail was making sure that my sample size was not too small. You're doing the exact same thing here. It's just you don't have to calculate anything. Okay, so the rule for means is simply that the sample size n must be greater than or equal to 30, okay, or the population is approximately normal. Okay, that's why it's called large counts, because you have a number, a count that you have to hit for the sample size. Okay, this is a big deal. Okay, and the central limit theorem is very commonly asked about on the AP test because it's this fundamental theorem of statistics. Okay, and it goes back to what we talked about in the previous slide when we were talking about the shape of the sampling distribution. Okay, even if the population is skewed, the sampling distribution will be normal if the sample size is large enough. Okay. And like I said before, because a lot of the data that we look at in the real world is skewed, we don't have a lot of tools to use to analyze skewed distributions. But if we pull a sampling distribution, then we are able to analyze that using our normal distribution tools as long as the sample size is big enough. Okay. And through many, many years and trials and figuring stuff out about statistics, statisticians landed on the number 30, the sample size of 30. Okay, as long as the sample size is 30 or more, then the sampling distribution will be normal. Okay, or, right, or remember the population could also be approximately normal. If the population is normal, whoops, let me underline this because I think it's important. Actually, let's highlight it. That would be better. Okay. So if the population is skewed, sampling distribution will be normal as long as the sample is big enough. And then when you have a normal population, sampling distribution is also normal, even with small samples. Okay. So if you're going to take anything away from this video, one, it's the formulas for mean and standard deviation, okay? And second, it's this, the central limit theorem and these three conditions, right? Really, the first two conditions are they're kind of roped in to the central limit theorem, but the key point for the central limit theorem is this point right here, the sample size being greater than 30 or the population being approximately normal, okay, in order for the sampling distribution of means to be normal. Okay. All right, you guys. So that is it for this video. In the next one, I'm going to go through, I think I have two practice problems for you to show you how to break these problems down. It's the process, like I said at the start of this video, is very similar to what you did with proportions. We're just going to make a couple of swaps with formulas, right? The formulas are a little different for means, and we have this one condition, the success fail or large counts, which I really should write on here, that this is also called large counts. But you'll hear it called large counts sometimes, this one right here. So process will be basically the same. We're just going to make a couple of swaps with formulas and that one condition right there. Okay. All right. So I will see you guys in the next video. All right, bye, everybody.